When we're discussing about qualitative analysis, we're trying to look for an identity of a substance. If I were to talk about quantitative analysis, so quantitative analysis, I'm looking for amount of substance, like how much did you produce, how much was required to produce this much amount. Now, qualitative analysis, again, is to trying to find identity of a substance. Take a look at for this example here. In this image, you see farming going on. There's some factory, and that will accumulate a lot of heavy metals in our water, in underground water, and that contaminates the water. Well, we can't drink this very harmful water, so it goes into a wastewater treatment facility, something that looks like this, and they will try to identify what metals there are and also to get rid of them. And that's where the qualitative analysis comes from. Now, just as it's important as quantitative, meaning how much stuff are in there, it's important to also understand what is even in there to start with. So here is sort of like an experiment, a very simplified experiment that will help you understand what I mean by to identify the metal. So here in this test tube, there's cation A, cation B, and cation C. And they're cations because a lot of the metals are going to be positively charged. So these guys are mixed in with water and you can't see them. And so let me label this. So cation A, this and B and C, these are all in aqueous form. So you can't see it. But we add in what is called a precipitating agent. Precipitating agent would be something, another chemical that will cause a precipitation to occur, meaning a solid to form. So what I'm saying is, hey, this, you see this blue chemical has to combine with this green one. Well, when they combined together, what happened was it formed into a solid. So you see a solid here. So that precipitation agent is actually that green solid, the green spherical ball, and that will interact with the blue one. All right, so you can decant the liquid, meaning just take out the liquid part, and then that liquid would be this aqueous form. Well, this top is also aqueous too. Now there's still more metals present, and say now we want to target cation B. You add in a second precipitation agent, so it could be the same one but maybe more in concentration, and that causes the cation B to precipitate out because it interacted with that agent. So this is my solid again, or also known as the precipitate, and here's my aqueous. And then you decant the liquid again, and then you get rid of the solid, and now you have this, so on and so forth, right? So this is how you can take out the metals one at a time so that we get a clear and pure form of water or whatever substance that you're trying to purify. So let's do a learning check based on what we have learned so far. Here, we're bringing in a little bit of a calculation and some identification as well. A solution has a concentration of 0.20 molarity of lead and 0.10 molarity of copper. So if I were to draw this out, I'm going to have a test tube with lead and copper. And I'm going to be adding iodide drop by drop. So I'm going to be adding iodide drop by drop very slowly. The question here is, if iodine is slowly added drop by drop, will lead 2 iodide form, or copper 1 iodide precipitate out first? So which one's going to come into solid? So if this were to occur in some time and point, you're going to have a solid in this aqueous form. Well, is this solid lead iodide or is this copper iodide? is the question that we're at hand, okay? When you're asked something like this, you're going to be looking and comparing at the KSP. So I already gave you the KSP for copper iodide. That's because it's not in the reference sheet, but go ahead and look for the KSP value for lead iodide. You'll notice that KSP, I actually have it written down here for lead iodide, that would be 7.1 times 10 to the negative 9. Having a much lower concentration of the solubility lets me know that this is the one that will precipitate out first. They don't want to be in the ion format. They rather be in the solid. Then your lead iodide will come out next. So here, the question at hand is copper iodide will precipitate out first. And again, you just compare the KSP value, and whatever the lower the KSP value, which is in this case copper iodide, is the one that's going to precipitate out first. And that's the easy part. Now we get into the calculation. I mean, it's not too challenging. Now, if iodide is added to the final concentration of 1 times 10 to the negative 5 molarity, what percent of copper will remain in solution? So even though not all of the copper iodide has potentially been there, and you might have some remaining copper in the test tube. So how much of that? What's the percentage? So let's go do the percentage calculation. First, go ahead and write the chemical equation of copper iodide going into solution. We have copper plus iodide in aqueous format. And then what you're going to do is write the expression for solubility equilibrium here. So we have copper plus and iodide negative. So we know the concentration of iodide, and that would be 1 times 10 to the negative 5. We know the KSP value, which is 1.0 times 10 to the negative 12. And we don't know the concentration of copper when it has reached equilibrium. We do know the concentration initially, but we don't know after equilibrium has passed, what is the concentration left over. So let's go ahead and divide this by 10 to the negative 5 both sides. Okay, and then we're going to get rid of, and then if you punch this into the calculator, you should get copper, not 2 plus, but plus, concentration of 1.0 times 10 to the negative 7. All right, so now we're here, and this is in molarity. If you want to know the percentage remaining, you take the copper final, concentration final, and then you're going to take the copper concentration initial and multiply by 100. So go ahead and plug this in and come back and see if you got it correctly. And here is the key. Very little percentage will remain in the precipitate.